Good morning to all. This is session 3 of module 3, and in this session we will discuss about various types of heat treatments. Let us move on to the first heat treatment and most popular type of heat treatment, that is annealing. Before going to annealing, let us study the part of this iron carbon diagram. This is a part of iron carbon diagram, and this part we have selected from 0 to 1.6 percent of carbon. Why? Because this is the percentage up to which the steel contains the carbon, and above this 1.6% of carbon, so the steel will become a cast iron, and cast iron is not amicable for the heat treatment as that of the steel. And coming to the various phases of this diagram is that this is, we know that this is the this is lower critical temperature line, and this is the point where eutectoid reaction will take place. In the eutectoid reaction, the austenite, it's a solid state reaction. The austenite is dissolved into alpha ferrite and iron carbide, and from 0 to 0.8 is called as hyper hypoeutectoid steels, and this is hypereutectoid steels. So above this line we have austenite phase, austenite phase, and then as the temperature decreases, the austenite is transferred into alpha and austenite, and then alpha into perlite. Similarly, this side, that is hypereutectoid steels, the austenite is decomposed into austenite and then iron carbide, and at the room temperature it is perlite and iron carbide. So these are the various phase transformations that is possible in the annealing. And before going to study the details of annealing, let us look into the various temperature aspects of the iron carbon diagram. Upper critical temperature, that is A3 point, that is A3 point. So this is the upper critical temperature. This is also upper critical temperature, and this is the lower critical temperature. Let us see the significance of upper critical temperature. A3 is the temperature above which ferrite starts to form as a result of ejection from the austenite in the hypoeutectile steel. So that whatever I said. So as the temperature decreases, the solubility of carbon in iron decreases, and excess amount will come out and forms and results in the formation of what is alpha ferrite and alpha ferrite. The upper critical temperature ACM is the temperature below which cementite starts forming as a result of ejection from the austenite in the hypereutectoid steels. This side, formation of cementite, and then lower critical temperature A1 is the temperature of the austenite to perlite, and where eutectoid transformation will take place. This is what the lower critical temperature, or it is also called as eutectoid temperature. And then below this temperature, below A1, austenite does not exist, or austenite is not stable. Austenite is not stable. Below A1 line, austenite is not stable. So these are the terms involved in the heat treatment. So every time we will not specify the particular temperature. We will say it is above a lower critical temperature or above the upper critical temperature. So coming to the annealing, heating of metal or alloy to a predetermined temperature, cooled at this temperature and finally cooled at a very slow rate, that may be within the furnace or within the atmosphere. So this is what the cycles involved in the annealing. So heat to a particular temperature and hold it or soak it, and then cool it very slowly. Usually the cooling is done in the furnace itself. So coming to the objectives, to relieve internal stresses developed during the solidification, machining, forging, rolling and welding, etc. So generally when the metals are subjected to the forming process or machining process, so the structure will be destroyed and it results in a collection of internal stresses that has to be removed before the component actually using for the purpose. So that is the first object. To improve or restore the ductility and toughness. So once the structure is destroyed, as the structure is destroyed, naturally the ductility and the toughness also decreases. This is also done to improve to enhance the machinability and to eliminate chemical non-uniformity. So if the composition is not uniform throughout the material, and under that case also people will use annealing process to make the composition uniform, to refine grain size and grain structure. So to control, to reduce or increase the grain size, we will use annealing, and to enhance the magnetic and electrical properties, of course, to reduce the gas content in the steel. So these are the various objectives of the annealing. So based on the temperature, the annealing can be classified into three types. One is a full annealing, partial annealing or incomplete annealing, or subcritical annealing. So look at this diagram. If the process in the annealing process, if the temperature is heated above A3, that is upper critical temperature, the corresponding process is called as full annealing. And if the temperature in the annealing process is below lower critical temperature line, then it is called as subcritical annealing. And if the temperature is between upper and lower critical temperature, then it is called as partial annealing. So these are the classification of annealing process based on the temperature. But in actual practice, annealing is classified based on the application. So that while that we will study uh, the types of annealing. So in general, what how the annealing process, what are the things in annealing process involves? Heating the steel to 30 to 50 degrees centigrade above A3 critical temperature of the A3 critical temperature of the steel. Maintain the temperature for a specified time period. Allow the material to slowly cool down inside the furnace. And some of the components or products that are annealed are hot worked steels, forgings, castings made from the medium and high carbon steels, and are the some of the examples for the annealing. Let us move on to the various types of annealing process. First one is recrystallization annealing. So in this process, the temperature is above A1 and held it for sufficient time. And when you held it for sufficient time, what happens? New stress-free grains will be formed. And the things involved in the recrystallization annealing are all heavy cold worked sheets are subjected to this treatment. This process consists of heating the steel above the recrystallization temperature, hold it at this temperature, and cooling thereafter. It results in decrease of hardness and strength and increases the ductility. So the outcome of the recrystallization annealing is decreases the hardness or strength and increases the ductility. The treatment is very important and it is frequently employed in industries manufacturing steel wires, sheets, and strips. The final structure of the treatment consists of free grain, strain-free grains. That is why it is called as a recrystallization annealing. And the larger the degree of freedom, lower is the recrystallization temperature. That means during heat treatment, if there is no any restriction for the deformation, under that case the temperature requirement decreases. Recrystallization can be achieved at a lower temperature by increasing the holding time. Generally, people will do this. Why? Because in order to reduce the cycle time, they will increase the soaking temperature and then decreases the soaking time. So that's in this way they can decrease the cycle time. In this process, temperature is predominant here. It is always desirable to raise the recrystallization temperature instead of increasing the holding time. Naturally, this is recommended, but in order to increase the production rate or in order to speed up the things, people will follow the other way. High carbon steels and high alloy steels requires higher recrystallization temperature. High carbon and high alloy steels requires higher recrystallization temperature. But naturally, when the carbon is added and alloys are added, what happens? The melting point is also increases. So when the melting point increases, so what happens? The recrystallization temperature also increases. In that sense, he says that the recrystallization temperature increases. And the other type of the second type of annealing is spheroidizing annealing. It is used to get the spheroids or globular of carbides, which improves the missionability. So the idea is not just to get a globular form of carbides. The whole idea is to increase the missionability of the material, especially high carbon steels. And this is possible when the grains will take the shape of spheres. Cementite of cementite of laminar perlite in case of hypoeutectoid and eutectoid steels, and both laminar and free cementite in the case of hypereutectoid steels collagens into tiny spheroids. This is how the spheroidal grains are produced. The degree of spheroidization depends on the heat treatment temperature and time. So the degree of spheroidization means how many per the definite area depends on temperature and time. This process can be completed in a short time by increasing the treatment temperature. Naturally, eutectoid steels are held about 20 to 30 300 degrees centigrade above the lower critical temperature, and then hypoeutectoid steels are heated 30 to 500 degrees centigrade above lower critical temperature. Because of the higher carbon content, hypereutectoid steels needs high temperature. High carbon steels and alloys are frequently spheroid in order to improve the missionability and ductility. Low carbon steels are not generally spheroidized. In case if I do, what happens? Low carbon steels are spheroid, they becomes very soft and gummy or sticky. So and this spheroidization is not at all recommended for the low carbon steels. And next, we will move on to other type of annealing, that is full annealing. The steel is heated above A3 for hypoeutectoid steels, and then above A1 for hypereutectoid steels. Hold it there. Then steel is furnace cooled to obtain chorus sphere light. When you obtain a chorus sphere light, then what happens? Chorus sphere light as decreases the hardness and increases the ductility. Not and don't heat above ACM to avoid continuous network of proeutectoid. Not to eliminate the formation, don't heat above ACM. So if you eat, then what happens? Cementite along the grain boundaries. So it results in cementite along the grain boundaries. So the presence of cementite in the grain boundary is not recommended. Why? Because it encourages the crack propagation. And the other type of annealing is partial annealing. It refers as a incomplete annealing or intercritical annealing. In this process, steel is heated between lower critical temperature and then upper critical temperature. It is followed by slow cooling. Annealing is always slow cooling. Generally, hypereutectoid steels are subjected to this treatment. The resultant microstructure consists of fine perlite and cementite instead of porous perlite. And the other type of annealing is diffusion annealing. And this diffusion annealing usually they perform to bring uniformity in the composition, also known as homogenizing annealing, employed to remove any non-structural uniformity. Steel is heated above the upper critical temperature, say within this range. The steel is held at this temperature for 10 to 20 hours approximately. The reason for this is that the grain refinement takes place at a temperature about 10 to 300 degrees centigrade above AC1 for hypoeutectoid steels. As low temperature are involved in this process, it is less expensive compared to the full annealing, which involves higher temperature. Hypoeutectoid steels are also subjected to this treatment in order to improve the miscibility. Steel with porous grains are suitable for this treatment. Homogenized steels is obtained by this process as a result of diffusion. So when you raise the temperature and you soak the material at high temperature for a very long time, then what happens? The variation in the composition itself causes the what you call change in concentration gradient, and because of the supplied energy, what happens? The content will try to take a uniform positions. In other words, I can say the contents or composition or alloying elements or even carbon will move from higher concentration points to lower concentration points and results in homogeneous composition. But heating to this heating to such a high temperature results in corrosioning of the austenite grains. That means the size of the grains will be increased. So with this, we can see some of the multi-choice questions. Let us say A3 is the temperature line. A3 is the temperature line is dash. Is it upper critical temperature line, lower critical temperature line, bottom critical temperature line, A and 3 temperature line. So A3 is the upper critical temperature line. Answer is A. Which of the following is not the objectives of annealing? To improve or restore ductility of the ductility and toughness. Yes, it's the objective. To enhance the machinability. This is also objective. To eliminate the chemical non-uniformity. This is also objective. To increase the hardness. So which of the not the objectives? So to increase the hardness cannot be increased by annealing. Hence the answer for 13 is D. Larger the degree of deformation, larger the degree of deformation, dash is the recrystallization temperature. So this we have seen. Dash is the temperature. Larger the degree, what happens? Lower will be the temperature. So low will be the temperature. Spheroidizing annealing is done on low carbon steels, high carbon steels, medium carbon steels, and aluminum alloys. D is not at all related. Low carbon steel cannot be done. Why? Because the carbon content is less here, and we left with two things: high carbon steels and medium carbon steels. And what do you call this? Iron ferrite is possible very much in the iron carbon steels, high carbon steels. Hence, the answer is high carbon steels. Annealing process employed to remove any non-structural uniformity. Which annealing process employed to remove any non-structural uniformity. So which is he is asking which is the annealing process that we will use to bring the compositional uniformity. So that is full annealing is different. Process annealing is not. Spheroidizing is for different purpose, and the answer is diffusion annealing process. The name itself, diffusion annealing process. Diffusion means movement of the atoms from one place to the another place depending upon the change in concentration gradient. So these are the objectives and answers I have given here, and I hope I have completed the session 3 of the module 3. Thank you very much.